Hello and welcome to Calculus Lesson 7.5, the cross product and its properties. So let's do a recall first. So recall, we have so far learned about the dot product and we have investigated it to quite a bit of extent. Okay, so the dot product says that if you have two vectors, u and v, and let's say that we take those vectors u and v and we place them tail to tail, then we can denote the angle between them as being angle theta. And we can represent the dot product in one of two ways. So one way is u dot v is equal to the magnitude of u times the magnitude of v times cosine of the angle between them. And of course, well, the other way to do it, it depends on how many dimensions u and v have. It could be u1 times v1 plus u2 times v2 plus u3 times v3. So that can be another method to represent it. This is just one of those two ways. And a couple of important things. The dot product always returns a number. So it returns a scalar quantity. And in reality, what the dot product is telling us is it's telling us the interactions between similar dimensions, x with x, y with y, is that what's said? Okay, so now we are moving on to cross product. So once again, we're going to assume we have two vectors. So assuming we have vector u and v, and let's say we place those vectors tail to tail such that the angle between them is theta, I can figure out the magnitude of something called the cross product. So notice that with the dot product, I had a dot. With cross product, I have a cross. Okay, like it just looks like a multiplication symbol. When you put the x between two vectors, it means cross product. Now notice here I put the absolute value symbols on the left and right. This is because I'm only looking for the magnitude, and I'll explain why in a moment. But nonetheless, the magnitude of the cross product is the magnitude of vector u times the magnitude of vector v times sine of the angle theta when they're placed tail to tail. This looks similar yet different than this. Okay, first things first, I'm only looking for the magnitude here. And that's equal to the product of the two vectors times sine of the angle compared to cosine. Now, why did I put the magnitude symbol here and not on the left? The reason is dot product automatically returns a scalar quantity. Cross product returns a vector quantity. Okay, so what this expression does is it tells us the magnitude of that vector. And in order to determine the direction, we have to use something called a right-hand rule. So this is just the magnitude. Okay, so the direction is determined using the right-hand rule, which is often abbreviated as RHR. Now, those of you that studied physics, you have done this to death, and now we are going to be doing it again. So just bear with me as I attempt to draw a right hand. So here I've got my right thumb, and I've got some fingers. So there's 1, 2, 3, and 4. Oh boy, maybe I should attend art school in the summer. So here we go. Here's our hand. Now, let's say your vector u is pointing in this direction, and vector v is pointing in this direction. So it's coming somewhat out of the page. They're not necessarily perpendicular, but it's not pointing in the same direction as you. So the way right-hand rule works is this. You take your right hand, as you would imagine, and your right fingers, you start pointing them in the direction of the first vector in the cross product. So here, the first vector in my cross product is u. So I would point my right fingers towards u. I then take my right fingers and I curl them towards the second vector, which is v, that's pointing away. So it's pointing out of the page. So I curl my right fingers like this. Okay. So I can't curl my fingers naturally backward. They have to naturally curl toward v. Okay. And in order for my right hand to naturally curl toward v, my thumb, notice it's now pointing up. It's pointing perpendicular to both u and v. And so the direction of your right thumb tells you the direction of u cross v. So U cross V direction comes from your right thumb. Now just think about that for a second. Okay, so if U cross V and your thumb points up, well, what about V cross U? Well, that's what we're going to investigate as part of the next example. So we will continue using the right-hand rule. Let's formally get into example 1. Okay, so let's say I have these two vectors and they're already placed tail to tail. And I know that vector U has magnitude of 20. I know that vector V has a magnitude of 30. And I know that the angle between them is 40 degrees. So I have to answer a couple of questions. The first question I have to answer is, well, what is U cross V? Now, I just want to mention something. Just like with a dot product, there were actually two ways to calculate it. This was one of the two ways, and the other way involves taking the sum of the products of each individual dimension. With cross product, this is also one way of determining it. Now, sure enough, that's just the magnitude, the direction you find like this, but together that only constitutes one method. And that method relies on knowing the magnitudes, right? So if you don't know the magnitudes and you just know the vector components, there's actually another way that we're going to learn how to take the cross product. So for now, we have the magnitudes given in the question, so that's why we fall to that formula automatically. Okay, so we are looking for U cross V, so we're going to find the magnitude first. We'll find the direction using right-hand rule. So the magnitude of U cross V is the magnitude of U times the magnitude of V times sine of the angle. Now, I guess this can get a little bit confusing. I guess this tip may or may not help you. This is how I remember. It might seem a little confusing, but cross product starts with a C, but it has the opposite trigonometric ratio. So it has the trigonometric ratio that does not begin with the C. So cross product, sine, dot product would be the other one, which is cosine. So whatever you can do to remember that. All right, magnitude of U is 20, magnitude of V is 30, and sine of theta, that's sine of 40. Okay, now, theoretically, if you had the vector components, you could easily find magnitude of U and magnitude of V, but then how would you find the angle between them? Well, then you would have to use dot product, and it would be a long process. So again, we'll learn another way to do this using just the vectors later. So 20 times 30 times sine 40, make sure your calculator is in degrees. Okay, so we have 386 apparently. So 386. Okay. Now, I'm not given any units here, so I'm not going to bother with that, but I have to give a direction. So that's the magnitude, the direction. So now I'm just going to write U cross V without the absolute value symbols. It's 386. The direction, so take your right hand, your right fingers are pointing in the direction of vector U. So now just try something for a moment. Imagine my thumb was still pointing up. So my right fingers are pointing in the direction of U. They need to curl towards V, but my fingers don't naturally curl backwards. They naturally curl to the left, right? Like this. So that means I have to change the orientation of my hand so that my thumb points into the page. Watch this. Now my right fingers are pointing in the direction U, and now they can easily curl towards V. And in order to do that, my right thumb points into the page. Okay, so there's a three-dimensional rendering. Now into the page we represent with an X inside of a circle. So this is two different ways to represent three-dimensional directions. So if I want to represent that something's going into the page, I would represent it with an X inside of a circle. If I want to represent that something is going out of the page, I represent it with a dot inside of a circle. Okay. So the way you remember this would be an arrow's crosshairs moving away from you. This would be the arrow's tip coming out towards you. Okay, so this is 386 into the page. Okay, so that's part A, U cross V. Now we're going to do part B, which is to determine V cross U. So essentially what we're trying to do here is determine whether the cross product is commutative. And if you recall, the dot product is commutative. So let's see if the same is true here. So magnitude of V cross U is going to be magnitude of V times magnitude of U times sine of the angle between them when placed tail to tail. Well, guess what? The angle doesn't change, therefore the sign of the angle won't change. And if you do magnitude of u times magnitude of v or v times u, it doesn't matter because multiplication is commutative. So that means the result of this will be the same as what we had up here, which is 386. Now, before you jump the gun here and say, well, that means cross product is commutative, you got to be a little careful here because cross product, remember, returns a vector, and vectors have direction. Just because the magnitudes are the same doesn't mean they're the same vector. They have to also have the same direction, right? This one's direction is going into the page. Now, if we do v cross u, now v comes first. That means when I use my right hand rule, I have to start my fingers of my right hand pointing in the direction v and then curl towards u. So take your right hand. Okay, so my right fingers are angled in the direction v first, and now if they curl towards u, sure enough, my right thumb is pointing up and out of the page. Okay, so this time my direction is out of the page. Now, these are definitely not the same thing, so that's the first thing I notice. I notice that the cross product is not commutative. So let me actually write that down first. Cross product is not commutative. Like addition's commutative, multiplication's commutative. Division and subtraction are not, and cross product is not commutative. But dot product is commutative. So remember that dot product is, but cross product is not. Okay, so what that means is u cross v, while it does not equal v cross u, it does equal the following. U cross v is equal to negative v cross u. Okay, I can make that statement because of what I've just determined. Notice they have the same magnitude, but the direction is opposite. So x is the negative direction of the dot, and the dot is the negative direction of the x. Just as east is the negative west and negative south is north, that's what this is implying. So if I put a negative with an x, that means it's a positive dot. That's what this statement means. Okay, but I know that u dot v is equal to v dot u. Okay, so that's the same statement I have here, just written mathematically. The last thing I want to show you for this example is the following. This is one way to represent the three-dimensional direction. Another is using a unit vector. Remember, unit vectors have magnitude 1 and they're going in a certain direction. Now, a popular unit vector we can use is n hat. That's a lowercase n. Okay, so we can say let n hat be a unit vector perpendicular and outward from the page. So if n hat is perpendicular and outward from the page, that means that, well, which one of these is going outward from the page? It's the dot. Okay, so that means this one I can also represent as 386 n hat. And since this cross product here, u cross v, it's going into the page, that means it's going in the negative n hat direction. So this would be negative 386 n hat. So just another way to represent the same thing. Okay, so that was the simple representation of cross product. And just like I said, dot product has two methods of determining it. Cross product also has two methods of determining it. Okay, so this is how we're going to do it. Recall. Okay, so let's say you have two vectors. You have vector u, and this is in R3. So we have u1, u2, u3, and you have vector v, which is v1, comma v2, comma v3. We can define the dot product between u and v another way. And we can define it as u1 times v1 plus u2 times v2 plus u3 times v3. Now, cross product can also be represented using a formula. Now, some people want to memorize this formula. Others, they'll use a trick that I'm going to show you on a way to solve the cross product without having to memorize this formula. Okay, so remember, cross product returns a vector. This is clearly a number plus a number plus a number. This has to return a vector, so I'm going to put these large square brackets and I'm going to put commas in between to separate the x, y, and z components. The x component of the vector is going to be u2 v3 minus u3 v2. Okay? And then the y component is going to be u3, excuse me, u3 v1 minus u1 v3. And the z component is going to be u1 v2 minus u2 v1. Okay, like I said, you can memorize that, or I'll show you another way to remember how to do this. The first time I show you, you might actually think it's a little bit of overkill, but the more you do it, the faster you'll get, and you'll find that this method might actually be a little easier. Okay, so what you do is you're going to take the three letters I, J, K, and you're going to write them next to each other with a bit of a space in between, and you're going to write it twice. I, J, K, I, J, K. And I know at this point, usually students like to make a joke. I guess this means I'm just kidding, but I'm not, because this is actually a great way to do cross product. Okay, so I've got my vectors here. And you can put the vector symbols on top, you don't have to. Now, essentially what I'm doing here is setting up something like a table. The first row of that table has IJK, IJK. The second row of that table, what I'm going to do is enter the dimensions for U. So U1, U2, U3, and then I'm going to write it one more time, U1, U2, U3. The reason I'm writing U first is because I'm eventually trying to figure out an expression for U cross V. Not V cross U, but U cross V. Whatever one comes first, that goes on the second row. And whichever one comes second, that goes on the third row. So this one's components are V1, V2, V3, V1, V2, V3. Okay. So what I like to do at this point is I like to use two extra colors at this point because, well, as you probably have seen, I like to use different colors to help things stand out. What I'm going to do is start drawing some diagonals. And the first diagonal I'm going to draw is going to go from I through U2 to V3. It's going to go like this. Okay. The second diagonal is going to go from J through U3 to V1. Okay, so if you lined everything up, the arrow should go directly through the letters. And the last arrow with the purple is going to be K through U1 to V2. Okay, now grab another color. This time we're going to be drawing arrows to I, J, and K on the right, not from I, J, and K on the left. Okay, drawing the diagonal arrow to I on the right, it's going to start at V2, go through U3, and end up at I. And then the second will go starting at V3, go through U1, and end up at J. And the last will start at V1, go through U2, and end up at K. Okay, I know that looks a little bit crazy, but just go with it for a moment. This is what we're going to be doing essentially. Imagine I have the following four letters set up. A, B, C, D. What I'm doing is I'm drawing a purple arrow from top left to bottom right, and I'm drawing a pinkish fuchsia arrow from bottom left to top right. And what I'm doing here is I'm determining AB minus DC or minus CD, whatever you like. That's what I'm trying to, calculate here. So this is how I'm going to get my expression. So remember, the result of a cross product is a vector. So here's my vector, and that vector is going to have x, y, and z components. For x, the x component is associated with the I letters. The y component is associated with the J letter. And the z component is associated with the K letter. Okay, so we're going to do AB minus CD for each component. So let's start with I first. I is going to be U2 times V3, just like we have A times B. U2 times V3. And then minus, okay, now we're doing the upward arrow towards I, V2 times U3. All right, now for J. J is U3 times V1 minus V3 times U1. And finally, K for the Z, U1 V2 minus V1 U2. Okay, so notice that is the same formula we have up here. The only difference is sometimes they're written a little bit different, but that's okay because multiplication is commutative. So this is how I'm going to be solving the cross product expressions moving forward using this method. I encourage you to learn this method and understand how it's used. If you want to memorize the formula, you can, but just keep in mind there's always a risk that you can mix up the subscripts, which will throw everything off, and you cannot even get part marks for it at that point because you haven't shown any work. You've just jumped to the cross product. Actually, now that we're on that topic, if you are just planning on memorizing this formula, you have to state the formula first before you plug in the numbers. This is one way at least you can show your work. Okay, let's try an example. So example 2. So now this example is going to be a bit long. We're going to do a lot of things with these 3 vectors, but here they are. Vector A is going to be the vector 7, 1, -2. Vector B will be the vector 4, 3, 6. And vector C will be -1, 2, and 4. Okay, so here we go. So part A, find A cross B. Okay, so we're going to use what we just learned up here. If I'm looking for A cross B, remember the order matters. So A is first and then B is after. So A goes in row 2, B goes in row 3. But the first thing that I do is write IJK twice. Okay, so again, the vector A you write twice, and that goes in row 2. So 7, 1, -2, 7, 1, -2, and then B goes in the third row, 4, 3, 6, 4, 3, 6. And I'm going to take my colors and draw my arrows. Okay, so first arrow is going I1, 6, second arrow J -2, 4, third arrow K7, 3. All right, next set of arrows. We're going 3, -2I, 6, 7J, 4, 1K. Okay, so here we go. So A cross B, remember the result of a cross product is a vector. Now, what you have to be careful of is subtracting and the minus signs. So notice you're always taking the first product and subtracting from it the second product. But if one of these values or both of these values are negative, you can easily make a mistake computing this. So always plug in the numbers exactly as is. I do not encourage you to try to skip steps here and do it in your head because you can easily make a mistake. Okay, I'm actually going to do this down here because I need a lot of space. So A cross B is equal to, put my first bracket. Okay, so for the x component, it's 1 times 6 minus 3 times -2, comma. Now J, -2 times 4. Oh, sorry. There we go. J, -2 times 4 minus 6 times 7, comma. Now for the Z, K, 7 times 3 minus 4 times 1. This is also a way for you to show your work, by the way. Okay, so what do we have here? We have 6 minus -6, comma, and then we have -8 minus 42, comma, and then we have 21 minus 4. Okay, so not so bad. So we have 6 minus -6, that's 6 plus 6, which is 12. -8 minus 42, that's -50. And 21 minus 4, that's 17. So this is the dot product of A and B in that order. So now this is a vector, clearly. I mean, you could figure out a magnitude here. The direction would be given by the coordinates of these vectors. Now, something to understand, something that we saw in the first page is that let's say you had just the magnitude of this dot product. You would be able to figure out the direction using right-hand rule. And what we saw with right-hand rule is you take your right hand, you start your fingers pointing in the direction of the first vector, which would be A here, and you curl it towards B, and then your right thumb points in the direction of the cross product. Now, what you should notice is whether you're like this or you're like this, however your fingers are curling, wherever A and B are, or U and V, whatever the two vectors are, your thumb is always at 90 degrees to your fingers. Always, no matter whether you're going like this or like this. It's always perpendicular. So what that means is the vector that comes out of the cross product will always be orthogonal to both the original vectors. So the vector that comes out of cross product is orthogonal. Remember, that's the other word for perpendicular at 90 degrees to both A and B, or whatever your initial vectors are. So we are actually going to confirm this in the next part of the example. So here we go. Part B. Confirm that A cross B is orthogonal to A. Now A, we already know it's given in the original problem. A is right here, 7, 1, minus 2. I'll just write that here, 7, 1, minus 2. Now, this cross product, it's a new vector. I mean, you can call that D if you want, because C is already taken from the original question, but it's a new vector. So you can call it D with an arrow on top, Z with an arrow on top, whatever you want. That new vector is perpendicular to this. Now, something that I've been saying again and again is when you have two vectors that are perpendicular to each other, there's something very interesting that emerges from the dot product. The dot product between A cross B, so that new vector, and A must equal what? So just think about that for a moment. Pause the video if you want to think. But that dot product is going to equal 0. Not the 0 vector. Remember, dot product returns a scalar, so just 0. So what we're going to do now is look at the dot product of the A cross B dotted with A. So A cross B is just that new vector we found, 12 minus 50, 17. And we are going to dot that with vector A, 7, 1, minus 2. Okay, so for dot product, we take the sum of the products of each component. So that's 12 times 7 plus negative 50 times 1 plus 17 times minus 2. Okay, so not too bad. Now, sure enough, if you grab your calculator, so let's do that. 12 times 7 plus negative 50 times 1. Oh, of course, you don't have to multiply that, but just for the sake of being thorough, that should be plus 17 times negative 2. Sure enough, that's equal to 0. Okay, so therefore, they are indeed orthogonal. Okay. Let's do another part, part C. Determine A cross B plus C and A cross B plus A cross C. Now, what you should notice when you look at this problem is essentially what we're trying to see here is if the cross product follows the distributive property. Okay, so we noticed on the very first page that the cross product was not following the commutative property, right? It had the opposite direction, same magnitude. So now we're going to see if it follows the distributive property. Can I take the A cross and distribute it into the B and then also the plus C and obtain this? Well, we're going to find out. So let's figure out what A cross B plus C is first. We're going to compute what B plus C is first, get that new vector, and then cross that with A, but in the other direction, of course. So B plus C. Okay, so remember B and C are given in the original problem. So B is here, 4, 3, 6. C is negative 1, 2, 4. Okay, so 4, comma 3, comma 6 plus negative 1, comma 2, comma 4. Okay, so we know what this is going to be. The sum of two vectors is another vector. So 4 minus 1 is 3. 3 plus 2 is 5. 6 plus 4 is 10. So we're going to call this new vector D, because that's what it is. It's a new vector. And now we are going to take the cross product. So A cross B plus C. This is the same thing as A cross D. Okay, so effectively what I'm doing is 7, 1, minus 2 cross with 3, 5, 10. Right? Now, I'm going to use my handy dandy method to figure out how to do this. So let's go ahead and set up our cross product. I'm going to do it here a little bit smaller. Hopefully you can make it out okay. So I'm going to put I, J, K, I, J, K. Whatever vector comes first, that gets written in the second row. So that's 7, 1, minus 2, 7, 1, minus 2, and then this one, 3, 5, 10, 3, 5, 10. And at this point, I like to take my colors, and I'm going to start drawing my arrows. Feel free to pause the video, do this on your own, and then you can fast forward the video and see how you did. It's a good practice. Okay. So I know this is going to be a vector result, so I'm going to put my equal sign all the way over here, because I know I'm going to need the space. For x, it's going to be 1 times 10 minus 5 times negative 2, comma. For the y, negative 2 times 3 minus 10 times 7, comma, k, 7 times 5 minus 3 times 1. I had to just check there for a moment. It kind of looked like a 7 with the j there, but no, that's a 1. All right, there we go. Okay, so let's see what we got. We've got 10 minus negative 10. Okay, we've got negative 6 minus 70. And we've got 35 minus 3. Okay. So 10 minus negative 10, that's 10 plus 10, which is 20. Negative 6 minus 70 is minus 76. 35 minus 3, that's 32. Okay. So there's A cross B plus C. And we're trying to see if that's equal to A cross B plus A cross C. All right, so let me just write this here. This is A cross B plus C. Let's just circle that for now so we don't accidentally lose it, because there's a lot of stuff here. Now, before you think, oh my God, I'm going to have to do 2 more cross products and add them together, you don't have to do 2 more cross products, because I already know what A cross B is. Okay? A cross B, we figured out way back in part A of the problem, so let me actually just grab that. Oops. In part A, we found A cross B. It was 12 minus 50, 17. So I just have to figure out what A cross C is, get that vector, and add it to this one. Okay, so let's do that. I'm just going to do a separation here so I can keep my work separate. Okay, let's figure out A cross C. Okay, so C, well, let's see. C is right there. It's negative 1, 2, 4. And A, we already have also, there it is, 7, 1, minus 2. Okay, so 7, 1, minus 2 crossed with, and where did C go again? Here we go, minus 1, 2, 4. Okay, so I'm going to do my IJK again. So A goes first, 7, 1, minus 2, 7, 1, minus 2, and C goes next, negative 1, 2, 4, negative 1, 2, 4. Okay, now grab your colors and do your arrows. So I1, 4, J, negative 2, negative 1, K, 7, 2, and 2 minus 2I, 4, 7J, negative 1, 1K. Okay, here we go. Let's do this here. A cross C is equal to, okay, so it's going to be 1 times 4 minus 2 times negative 2, comma, negative 2 times negative 1, minus 4 times 7, and comma, k, 7 times 2, minus negative 1 times 1. Okay. Oh my gosh, I'm sorry, you guys didn't see any of that. Well, there it is. All right, let's figure out what we got here. So we have 1 times 4, that's 4, minus 2 times negative 2, that's 4 minus negative 4. Negative 2 times negative 1, that's positive 2. 4 times 7 is 28. 7 times 2 is 14. Minus negative 1 times 1 is negative 1, so that's minus negative 1. And be careful with your signs here. So what does this equal overall? 4 minus negative 4, that's positive 8. 2 minus 28, that's minus 26. And 4 minus negative 1, that's 4 plus 1, which is 15. Okay, so we've got our vector here. That's A cross C. Now remember, the whole point of doing this was to see if A cross B plus C was the same thing as A cross B plus A cross C. So this is A cross C. Okay, so let's do A cross C plus A cross B. All right, so if we do that, A cross C is right here. 8, let me write that again. 8 minus 26, 15, plus A cross B. Again, we found that in part A. It was 12 minus 50, 17. So you just have to add up the vector components on their own. Okay, so A plus 12, that's 20. Minus 26 minus 50, that's minus 76. And 15 and 17, that's 32. Well, I hope that number sounds familiar to you because we got the exact same result right here. Okay, so that means that A cross B plus C is the same thing as A cross C plus A cross B. This tells us that the distributive property does indeed apply to cross product. So here's our results, and sure enough, they're the same. Okay, so let's summarize this. Let me grab another sheet here. Okay, so what we see is that therefore we can say that A cross B plus C is the same thing as A cross B plus A cross C. Just be careful with the order. Remember, the order of cross product matters. If A comes first and then you're crossing it with B plus C, it's A cross B first plus A cross C. And so likewise, so let's put and. If you have A plus B and you cross that with C, you also have to be mindful of the direction. It will be A cross C plus B cross C. Like this. And I'm just going to put a little star here to remind you that the order matters. So B cross C is not the same as C cross B. Okay, we are officially, well, halfway through the lesson. So let's keep going. Excuse me. Example 3. This is going to be a proof. Prove that for two non-zero vectors, u and v, where u cross v equals 0, this happens if and only if, so remember that's what IFF stands for, if and only if there is a scalar k, which is an element of the real numbers, such that U is equal to KV. All right, so let's understand what this question is stating first. You have two vectors, U and V. Now, you don't know what dimension you're dealing with, so let's just stick a dimension here. Let's say we're in R3, third dimension. Okay, so we have two non-zero vectors, U and V. We have to prove that if their cross product is 0, this only happens if they are scalar multiples of each other. Now think about that for a moment. Think about it from a different way before we even prove it. If two vectors are scalar multiples of each other, that means that they are going in the same direction or opposite direction, right? So that K value can be positive or it can be negative, but they're parallel to each other. And if two vectors are parallel, so if they're going in the same direction, what's theta? Theta is 0 degrees. And if they're going in opposite directions, theta is 180 degrees. Well, guess what? Cross product involves sine of theta, right? Magnitude of U times magnitude of V times sine of the angle between them. So if the angle between them is 0 or 180, guess what? Sine of 0 and sine of 180 is 0. So the cross product becomes 0. Now we have to show this via proof. So here we go. So let U, I have to define what U is first. U is going to be in R3, so it has three components, U1, U2, and U3. And vector V has components V1, V2, and V3. All right, and I know that U cross V is 0. This is my starting point, right? But not just any 0, it's the 0 vector, since the result of the cross product is a vector. Starting from this, I have to obtain this. Now, I'm dealing with cross product. There is a formula for cross product. Now again, you shouldn't need to memorize this. You can always derive it on the spot should you need it. So IJK, U1, U2, U3, U1, U2, U3, V1, V2, V3, V1, V2, V3. All right, now here are my colors and my arrows. There's my first set of arrows and my second set of arrows. Okay, so based on those arrows, I'm going to come up with my expression. So 0 vector is equal to U cross V. So U cross V is U2 V3 minus V2 U3, comma, J, U3 V1 minus V3 U1, comma, K, U1 V2 minus V1 U2. All right, so there we go. Now, what's the 0 vector? Well, the 0 vector in R3 looks like this. 0, 0, 0. Now, if I have two vectors equal to each other, that means that their x components have to be equal, the y components have to be equal, and the z components have to be equal. Okay, so what that means is this piece right here has to equal that 0. Okay, so U2 V3 minus V2 U3, that's equal to 0. And just for the same reason, the y component must also equal 0. So this also equals 0. And the z component, for the same reason, has to equal 0. This is what's going to set up our proof. So I'm going to make a set of 3 equations here. My first is U2 V3 minus V2 U3 equals 0. Right? So that comes directly from here. The next one is from here. U3 V1 minus V3 U1 equals to 0. And the last statement comes from this end. U1 V2 minus V1 U2 is equal to 0. Okay, so I'm going to just take the minus piece and bring it to the right side in each case. So U2 V3 equals V2 U3. U3 V1 equals V3 U1. And U1 V2 equals V1 U2. Gosh, it sounds like I'm repeating myself over and over again, but sure enough, I mean, there are the letters. Okay, so the next step I'm going to do here is get the same dimensions next to each other. So U2 with V2, U3 with V3, Okay, so in order to do that, I have to write it as a quotient. So I'm going to write u2 over v2 equals to u3 over v3. And on this middle piece, I'm going to have u3 over v3 equals u1 over v1. And finally, that last piece, I'm going to have u1 over v1 equals u2 over v2. Now check this part out. This is interesting. I see that u2 over v2 is equal to u3 over v3. But u3 over v3, that's over here too. And that's also equal to u1 over v1. Well, guess what? u1 over v1 is over here as well. And that's equal to u2 over v2, which is all the way over here, which is also equal to u3 v1. And so all of these expressions are equal to each other. And keep in mind that each one of those entries is just a number. So all of these entries, they are not only equal to each other, but they're equal to a constant. So then my next line is this. Therefore, u1 over v1 is equal to u2 over v2, which is equal to u3 over v3, and we're just going to call that k. K is a constant. So now if each of those is equal to the constant k, I'm going to make their own expressions. u1 over v1 is equal to k, u2 over v2 is equal to k, and u3 over v3 is equal to k. Right? They're all equal to k. So from u1 over v1 equals to k, I can multiply the v1 over. That means u1 is equal to k times v1. From the middle, I have u2 is equal to k times v2. And from the last, I have u3 is equal to k times v3. Now this is where it starts getting fun. All right, so get your vector. If you remember my original vector u, I state up here at the top, vector u is u1 comma u2 comma u3. So let's rewrite that down here. Vector u is equal to u1 comma u2 comma u3. Well, guess what? u1 is the same as k times v1, so I'm going to write that here. u2 is the same as k times v2, so that's going to go in the middle slot. And u3 is the same as k times v3, so that's going to go in the last slot. So kv1, comma kv2, comma kv3. Now, since every single dimension in the vector has the same scalar multiple, I can factor it out. Just as I can distribute the scalar multiple inside, I can factor it out. So that's equal to k v1, comma v2, comma v3. And sure enough, there you have it. The vector u is equal to a constant times the vector v. So therefore, u is equal to k times v. And we have proven that, well, these two vectors have a cross product of 0 if and only if a scalar k exists. So we should actually state k. K is an element of the real numbers. So this only works if the two vectors are scalar multiples of each other. Now, I'm going to show you this in a slightly different way. Okay, so we are going to, again, prove this working in the other direction now. Okay, so we just showed that if the cross product is 0, so starting with the fact that the cross product is 0, we ended up, so right here we started, we concluded that, therefore they are scalar multiples of each other. We are not going to prove it in the opposite direction. Starting with the fact that they're scalar multiples of each other, we're going to show that the dot product is 0. So here we go. U cross V. Well, I just showed that U is equal to a constant times V. So starting with that, so this time we're going to start with U is equal to K times V. So that means this is equal to K times V crossed with V. Okay, so K times, now vector V is just V1, comma V2, comma V3. And I'm going to cross that with V1, comma V2, comma V3. Now here I have the scalar multiple of vector V. Here I have just vector V. When I have the scalar multiple, I can take the constant k and multiply it inside to each term. So this becomes kv1, comma kv2, comma kv3. And I'm going to cross that with v1, comma v2, comma v3. So you know how to do cross product. You use that setup of ijk, ijk. So here we go. I, j, k, I, j, k. Okay, this is the first vector in the cross product, so it gets written in the second row. KV1, KV2, KV3, KV1, KV2, KV3. And then the second vector I write in the third row, V1, V2, V3, V1, V2, V3. All right, here we go, grabbing my colors, downward purple arrows, and upward pinkish arrows. Okay, so let's figure out what this cross product is going to be. It's for the x component, for I, it's KV2 times V3. In fact, I don't really have to use brackets because I don't have any negative numbers here, and they're all letters. So I'm going to actually stop using the brackets. So KV2 V3 minus V2 KV3. That's for x. For y, you have KV3 V1 minus V3 KV1. And then for z, you have KV1 V2 minus V1 KV2. Now you know multiplication is commutative. So KV2 V3 is the same thing as V2 KV3, right? They're just written in a different order. So the result of the x piece there, it's 0. And sure enough, if you follow that pattern for the y piece, KV3 V1 is the same thing as V3 KV1. So that's 0. And for the same reasoning, the component for z is also 0. And so we end up with a 0 vector. So proving this in reverse is also workable. So I want to put here a little bit of a summary. Recall, if the dot product between two vectors is 0, what does this mean? They are perpendicular. So that gave us a really important piece of information. Okay, so now what we have just seen is that if your cross product between two vectors is 0, that means they are parallel or they are collinear. Okay, so those are two very important properties. One more property that I'm going to show you before we move on to the last example, last quarter of the lesson. So one more property to show you is that if you have a scalar multiple of the cross product of two vectors, so k times u cross v, well, you can take that scalar multiple and you can multiply it to the first vector and then take that cross product with the second vector. But what you can also do is you can take that first vector u and you can cross it with the scalar multiple times the second vector. So it works just the same. And if you understood how this formula comes about, the reason why this works should make sense. Okay, we're moving into our last example. Now it does comprise of two parts. So here we go, example 4. You know what? I might actually, you know what? No, I'll just write it on this page. Determine the area of the parallelogram defined by vector u, which is 4, 5, 2, and vector v, which is 3, 2, 7. So this is going to be part A. Not this part right here, that these are the vectors. This is part A. Okay, determine the area of the parallelogram. Now, if you're sitting there wondering, how on earth am I going to determine the area of a parallelogram? And what does this have to do with everything we've done so far in the lesson? Well, it turns out that the cross product's magnitude has a very interesting application. If you recall, when we were studying dot product, we saw that a really interesting application of dot product was being able to calculate work. So, for example, in physics, we say that if a force causes an object to undergo a displacement that is non-zero, and also you have to have a non-zero force, then work is done on the object and it has obtained energy. For cross product, we have to define the following. A is equal to magnitude of U cross V, and this A is the area of a parallelogram. So the area of a parallelogram is given by the magnitude of the cross products, which define two sides of a parallelogram. And of course, those two sides have to be non-parallel. Okay, so in order to find the cross product between two vectors, the magnitude, first we need the actual cross product. We can figure out the magnitude afterwards. So we need U cross V. Okay, so that means we need 4, 5, 2 cross 3, 2, 7. Now, since we're finding the magnitude, it doesn't really matter which order you do it, although just for the sake of being complete and thorough, I like to keep it the same. Okay, so here we go, I, J, K, I, J, K. So here we go, 4, 5, 2, 4, 5, 2, and then 3, 2, 7, 3, 2, 7. Okay, I'm going to draw my arrows in now. And so there's my downward arrows, upward arrows. Okay, now the result of this is going to be a vector, right? So here we go. For the x component, you know what, I'm not going to commentate or put a commentary here. Try to do it on your own and then check up every now and then to make sure you're doing it right. Okay, so if you need more time, pause the video, but otherwise please look up and see, make sure what you have matches what I have. Okay, let me grab another piece of paper here. Okay, so 15 times 7, sorry, 5 times 7. Okay, that's a little bit easier to calculate. 5 times 7, that's 35, minus 2 times 2, which is 4. 2 times 3 is 6. 7 times 4 is 28, so 6 minus 28. 4 times 2 is 8. 3 times 5 is 15. So this is what we're trying to figure out. All right, 35 minus 4, that's 31. 6 minus 28, that's minus 22. And 8 minus 15, that's negative 7. So that's our cross product. In order to find the area, we need the magnitude. So A is equal to the magnitude of U cross V. So we're looking for the magnitude of the vector 31 minus 22 minus 7. So how do we find magnitude? It's been a while since we did this. We take the square root of the sum of the squares of each component. So the square root of 31 squared plus negative 22 squared plus negative 7 squared. All right, this, we're going to use our handy dandy calculator. 31 squared plus, and again, you know, it doesn't matter whether you put plus or minus 22 and square it, it's going to be positive, but let's just do this. So we have 1494, and so it's going to be root 1494, and if we actually take the square root of that, it's about 39. Let's just call that 39. 39 square units. All right. Part B. Let me just box this. Determine the angle between U and V. Okay. Well, normally when we are finding the angle between two vectors, we use dot product. And normally that would be fine, and you could theoretically do that here, but it would take a lot of work and a lot of steps, unnecessary steps. We already know what the cross product is, so if we use our other definition for the magnitude of a cross product, magnitude of u cross v, so this is the first one we learned. It's equal to magnitude of u times magnitude of v times sine of the angle between them. So if we're looking for the angle, let's isolate for sine theta. So sine theta is equal to magnitude u cross v divided by magnitude u, magnitude v. And guess what? We already have the magnitude of u cross v, so there's our numerator, 39, or you can keep it as root 1494. We just have to figure out what magnitude of u and magnitude of v are. So magnitude of u is going to be the square root of the sum of the squares of vector u, and vector u is right here, 4, 5, 2. So 4 squared plus 5 squared plus 2 squared. And magnitude of vector v, it's going to be the same thing, just with the v components. So that's 3 squared plus 2 squared plus 7 squared. Okay, so 4 squared is 16, 5 squared is 25, 2 squared is 4. If you add all of those, you're going to get 45. So root 45. 3 squared, that's 9, plus 4, plus 49. Okay, that's going to be root 62. Okay, so now we have the values to plug in our formula here. So the top is root 1494. You can plug in the 39 if you want. I just want to keep it exact till the last step. Times root 45, root 62. And here we go. Root 1494 divided by root 45 times root 62. 0.732, take the inverse sine of that, and we have about 47 degrees. With the angle, giving it to the nearest degree is fine. Okay, so this is the angle between the two vectors. All right, so that concludes our lesson today for 7.5, the cross product and its properties. Stay tuned for the next video in this chapter 7.6.